All right, continuing on with section 4, we get to Lusac's law. So you're going to start to see some patterns as we go through some of these gas laws, because they're all just derivatives of the combined gas law that I showed you earlier. So Lusac's law is looking at the relationship between pressure and temperature. So that assumes that volume in number of moles is held constant. If you look at the equation, it looks very similar to Charles' law. Okay, so we see that pressure is on the top instead of volume. Temperature on the bottom still needs to be in Kelvin, but notice since it's set up like this, it's still a direct relationship. If pressure increases, so does temperature. And so let's take a look at an example problem. Suppose the pressure of a gas goes from 1 atmosphere to 3 atmospheres. If the original temperature was 200 Kelvin, what is the new temperature? And I give you a hint, can you use the relationship? So what do I notice about the pressure? The pressure goes from 1 atmosphere to 3 atmospheres. In other words, the pressure is tripling, right? So if I, think about 3P. Well, what's the relationship between pressure and temperature? It's direct, right? So if the pressure triples, so does the temperature. But the temperature triples in Kelvin, not in Celsius. Well, good news, it gives us the temperature in Kelvin. So if the pressure triples, the Kelvin must also triple. So the new temperature would actually end up being 600 Kelvin. Notice I didn't have to use any equation. I would have gotten the same answer if I had used the equation, but I didn't have to. I was able to rely on my relationships. And you're going to see that as long as you know the gas relationships, they may come in handy, depending on how the question's worded. So keep that in mind. Sometimes students have a question on this. They say, well, what if you asked us this question on an exam? Do we have to show work? You either A, have to show work, or if you just wrote 600 Kelvin, you would want to at least write out, write out the 3P times 3T, or to some extent, I need to know that you're using the relationship. So just make sure that you add something in there and you don't just leave, the number. All right. And then the last law, Avogadro's law. So Avogadro's law is looking at the relationship between volume and moles. And so that assumes pressure and temperature are constant. Notice how it's set up. Once again, looks very similar to the last two that we saw. So for example, Avogadro's law, instead of having volume over temperature, it's volume over number of moles. But it's still a direct relationship. So anytime you have the variables on top of each other like this, that's going to be a direct relationship. So they're both going to increase or decrease in the same direction. All right, continuing on with Avogadro's law. Avogadro, first of all, looks kind of creepy, but we're going to not talk about that. Avogadro's law is actually very useful as long as you understand what he discovered. So in addition to that equation we just saw, he discovered or proposed that as long as the temperature and the pressure are the same, meaning they're not changing. So not temperature and pressure are the same number, but as long as you're at the same temperature and same pressure, meaning they're not changing, then he proposed that equal volumes of different gases will contain the same amount of particles. Okay, so let's digest that. Let's make sure you understand what he's saying there. So let's just come up with a random pressure and a random temperature. I'm totally going to make stuff up. Okay, so let's just say the pressure is 783 torr and the temperature was 303 Kelvin. I'm totally making stuff up. It doesn't matter. So what he's saying is, okay, as long as that pressure and temperature remains constant, it doesn't change, the room doesn't, get hotter or the temperature get all crazy, then as long as that pressure and temperature are constant, they're the same, then if you had different gases, so let's say you have hydrogen gas, nitrogen gas, and oxygen gas, these three gases, you would have equal volumes, and you would have, as long as the volumes were equal, let's say you had 1 liter of this gas, 1 liter of this gas, and 1 liter of this gas, he's saying, okay, the volumes are equal, and so therefore, there must be the same amount of particles in those balloons. Okay, so once again, as long as your pressure and your temperature are set, then as long as the volumes are equal, the number of moles will be equal. So that's a derivative of what he's saying right here. And so the balloons all have the same volume. This means they all contain the same number of molecules. That's actually pretty powerful. By the way, this is kind of where we got the idea of 1 mole of any gas will equal 22.41 liters. You remember me saying that? I was like, it doesn't matter what gas you have, as long as, you've got 1 mole, it'll occupy the same volume, and vice versa. There's that volume to mole connection. And that's pretty powerful. Okay, we can figure out a lot of things from knowing that. All right, so once again, remember this was the combined gas law. We saw this at the beginning of section 4. It shows how all of them are related to each other. And so remove out the variables that aren't mentioned in the problem, and you'll end up getting a simplified version of the equation that you need to use. And so what we're going to do is we are going to look at something that you'll actually have to do this on your exam 4. So this is example 9 in your notes. And so suppose you have a container of neon gas particles that are currently at a pressure of 3.00 atmospheres. What would be the new pressure in each of the following scenarios if the following conditions were changed? Assume all temperature changes are in Kelvin, which is good for us, it's nice to know that, and that any variable not mentioned is held constant. All right, so let's review the relationships between all of these variables. What was the relationship between pressure and volume? Do you remember? It was inverse, right? As one goes up, the other one goes down, right? The same actually is true, even though we never mentioned it, the same is also true for number of moles and temperature. So you see how they're next to each other? Moles and temperature are next to each other. That's how you know they're also inverses. So what variables are inverses of each other? Here, I'll write it out to the side. What are inverses of each other? Pressure and volume, and then moles and temperature. Those sets of variables are inverses to each other. As one goes up, the other one goes down. Well, what are the ones that are directly related to each other? What are the ones where if one variable goes up and increases, so does the other one? Any variables that are on top of each other. So for example, pressure and moles. That's direct. Pressure and temperature, because pressure and temperature are on top of each other. So is volume and moles. And so is volume and temperature. So those are your direct relationships. That's going to help us out when we do these problems down here. So let's look at the first one. If volume was doubled, okay, if volume was doubled, what would be the new temperature? So here's how you solve this problem. You say, okay, volume was doubled. What's the relationship between volume and pressure? Well, volume and pressure are inversely related. So if volume is doubled, that means pressure is cut in half. And so we say, okay, well, the original pressure was 3.00 atmospheres. So that means the new pressure would be 1.50 atmospheres. And that's how you would solve the problem. All right, let's look at the second one. Temperature was tripled. So I would write, and I'm going to do it up here, okay, temperature was tripled, 3T. What's the relationship between temperature and pressure? That's a direct relationship. So if temperature was tripled, that means pressure was also tripled. So if the original pressure was 3 atmospheres, 3 times 3 is 9. But I want to keep all my sig figs. Okay, I should have 3 sig figs, so it'd be 9.00 atmospheres. All right, let's make it a little bit harder. Let's look at number 3. Volume is cut in half and moles are doubled. So you're changing 2 things. So what happens when you're changing multiple things? Deal with them separately and then combine them together. So let's just focus right now on volume is cut in half. Let's just focus on that one. So I'm going to do this off the side. Let me get a different color here. All right. So if volume was cut in half, what would that do to the pressure? Well, volume and pressure are inversely related. So if volume is cut in half, pressure would double. Right? Now, let's focus on just the moles part. We did the volume, now let's do the moles. Moles is double, so 2N. What's the relationship between moles and pressure? Moles and pressure are direct. So if moles is doubled, so is pressure. And now you combine them. So, in the first one, pressure doubled, and in the second one, pressure also doubled. So take your coefficients, 2 and 2, and just multiply them together. that means collectively pressure will quadruple. That's how you do that. And so if pressure quadruples, and originally the pressure was 3 atmospheres, 4 times 3.00 atm ends up getting our new pressure of 12.0 atm. Notice how I keep 3 sig figs there. Okay, so the new pressure is 12.0 atmospheres. All right, let's go for the gusto. Let's get a really tough one, okay? And I'm going to give myself a little bit of space here. I'm going to erase some things so I can have more space to work this one out. All right, and we're done with this up here, so I guess I can get rid of all that too. All right, last one. Volume is tripled, temperature is doubled, and moles are cut in a fourth. Sure, yeah, let's do it all. All right, so take each one at a time. So first thing, volume is tripled, so 3V. What's that going to do to the pressure? It's going to cut it in a third because they're inversely related. All right, second one, temperature is doubled. Okay, so 2T. That's going to double your pressure because pressure and temperature are directly related. Finally, moles are cut in a fourth. So 1/4 moles. That means 1/4 pressure because pressure and moles are direct. So now we have to take into a consideration, we've got a third, we've got double, and we've got a quarter. So 1/3 times 2, which I'm going to write it 2/1, times 1/4 ends up being 2/12, which is the same thing as 1/6. So the new pressure is going to be a sixth of what it was. So I would just take 1/6 times the original pressure, which was 3.00 atm. Okay, and so I would end up multiplying that through, and I end up getting 0.500 atm. That would be the new pressure. Notice I have 3 sig figs here. This 0 does not count. 3 sig figs because 3.00 had 3 sig figs. So that was it. That was the most challenging one. But you just take each change separately and then you combine them together to get what the new pressure would be collectively. All right, that wraps up section 4. I'll see you in section 5.